Hello! You've probably heard about Big O notation for describing the runtime performance of algorithms. But do you know its formal definition? No? Well, don't worry. I'm here to help you understand your friends when they talk about the asymptotic complexity of their programs. Big O is called like that because it's written with a big O, and it stands for the order of a function. We'll call our function g of n. The order of a function just means the family of functions that are constant multiples of that function. They all really like each other because they're part of the same big uncountable family. Given two real valued functions f of n and g of n, we can say that f of n is of the order of g of n if and only if, given two constants c greater than 0 and n0 greater than or equal to 1, f of n is less than or equal to c times g of n for all n greater than or equal to n0. What the hell are you talking about, you might ask? I'll show you. If you're studying a function, you can bound it just by finding the constants c and n1. You can see a random function here, f of n in orange, and a function g of n in green. Because the green function has a higher rate of growth, we can easily find the constant n1 after which all images of g are greater than the images of f. But if we scale g by a constant smaller than 1, since the rate of growth is still higher than f, we need only find a big enough n2 after which the conditions meet again. This, combined with the fact that this polynomial is smaller than this polynomial, we can say that it's also smaller than this polynomial, making it order of n to the d. Thus, we don't need to include constants or lower order variables in our big O notation. Here are some common examples of functions used to bound the amount of steps needed to execute an algorithm. If your algorithm runs in constant time or in a of log n and actually accomplishes something interesting, congratulations! You designed a really efficient algorithm. Linear time is still kind of okay, and don't feel bad if your algorithm is O n log of n. It's been proven that n log of n is the fastest a comparison-based sorting algorithm can be. But if your function runs in a higher order polynomial, an exponential, or God forbid, a factorial time, you should think long and hard about what you've done. Now, this is probably the simplest algorithm I could think of, adding up all the numbers in a list of integers. It's made of a couple of single operations and a loop that walks through the whole list linearly. So as the size of the input grows, the runtime of this algorithm grows linearly. We can add the steps of the function like this. O of 1 plus n times 1 plus 1. And that just gives us O of n. Well, that's all for today, folks. I hope you enjoyed this short introduction to a quite complicated topic. But this is just the start of a journey. I will keep uploading videos and writing posts on my Patreon talking about a secret project I'm working on. See you then!